Last session, we started talking about optical flows and depth estimation. And the intuition behind this and why we are doing it is because the world around us is moving, is evolving over time. And at the same time, it's a 3D world. And then we talked about optical flows. We covered FlowNet. And then today we are going to continue that. But last session, there was a question about the color map and how do you actually use it to visualize 2D vectors. So first of all, what is optical flow about? Two images, two consecutive frames of a video are going to go in. Let's focus on the right arm of this person. Let's focus there. What is going to come out of your optical flow algorithm, or what you want it to produce, are these vectors. That this pixel is going to end up where in the other pixel, in the other frame. So where is going to be the location of this pixel in the other frame? And these arrows are going to enable you to actually do that analysis. If you take this pixel, use this arrow, the corresponding arrow, that's going to help you know where it's going to end up in the next frame. So in that way, you are modeling the movement of pixels in your image over time. The x coordinate, you can plot it here as an image. The y coordinate, you can plot it as another image. So these are one and two ways of visualizing optical flows. A nicer way of visualizing is using this color map. What are you doing? Look at the center. That's going to be a vector. From the center to any of these colors, you can put a vector, and then you can just read off the color corresponding to that vector from this color map. If a vector has a value of 0, it's actually a 0 vector, it's going to be white. And if a vector is pointing in the other direction, it's going to have a different color. And if it is longer, it's going to have a different color. And that's how you can visualize flows in your image, optical flows. For instance, most of the pixels in this image are not moving, so they're mostly white. And then a couple of them are moving. For instance, the pixels on this car are moving because the car is moving, and it's moving really fast. This other car is moving slower, and it has a red color, so it's probably pointing to the right. So that's how you're going to read that. Any questions about this? So is this clear now? Okay, perfect. The other one is about depth estimation. And that one we are going to cover after 3 slides today. And the idea is that if you look at this image, we as human beings are really good at localizing ourselves and localizing the other objects, how far they are from us. And that's why we are able to drive. We are able to move in an environment because we are good at localizing ourselves and localizing the other objects in the scene. And how do we do it is a question. And we want an artificial intelligence, which is going to be your self-driving car or your robots, to be able to do the same thing. One idea, which is not practical, is to put sensors on other cars, on all of these trees, everything, which is going to end up being too costly. You need to change the entire world. The other one is to put sensors on the car itself. And one of the cheapest sensors out there are just cameras. Just mount a camera on your car, which is going to end up being very cheap. And from an image, you want to estimate the corresponding depth, how far the objects are from you. And unlike optical flows, this is just a 1D thing or a 1D function that you're plotting. It's not 2D. You don't have X component or Y component anymore. Let's continue with optical flow. Last session, we covered FlowNet. One of the problems when it comes to optical flow estimation is that you don't have any good data because you don't have any good sensors to give you real data. One solution is to work with simulated data. And flying chairs is a simulated data. You just simulate the location of these chairs on still images, on background, on different backgrounds. And these are the corresponding ground truth flows. And these you can get basically for free, because you know the location of the chairs. You can write everything down mathematically, and you know the ground truth. We covered an architecture last session. It had some residual connections, and it was outputting our flow. You're going to train your algorithm on flying chairs, And then you're going to test it on something like Sintel data, which you have the ground truth for. These are animated or animations. And then you can also apply it to something like Kitty data. And the problem is our sensors are not perfect, so they're going to give us 50% of the pixels to have labels. Then we covered FlowNet 2, at least parts of it. We are trying to improve upon FlowNet 1 and try to solve these two problems. One is that you have some problems with the small displacements. When something is moving slightly, you are not able to approximate their flow correctly. The other one is you have these noisy artifacts in your flow estimation coming out of FlowNet. And if you try to study FlowNet more, you're gonna end up with these two conclusions. One of them was pre-training on chairs and fine-tunings on another, or fine-tuning on another data set, like things 3D is gonna help you a lot. Training for longer is gonna help a lot. The other one is a better architecture, also helps a lot. And these two architectures are already in FlowNet paper, but there is a catch with FlowNet C, is that it's too costly. And C stands for correlation. So what's gonna happen is you're gonna have two images. They're gonna go through your neural network, and you're gonna get two feature maps out of them. And then you can have a FlowNet C layer. What does that do? It's gonna compute the correlation between two patches centered around 2 pixels from this feature map and the other feature map. And this is the exact formula for it, for computing that correlation. We covered it last session. It has a computational cost that is quadratic in terms of the number of pixels. And that's why it's expensive. How can you reduce it? Rather than every single pixel, paying attention to every single pixel from the other feature map, your x2 could be in the neighborhood of x1. So just look locally. And D is your neighborhood. Now it's a hyperparameter that you can control. It means that you have your computational cost under your control now, to some extent. Now it's linear in terms of your resolution. Another solution is, rather than looking at every single pixel, you can look at every other pixel or every 2 pixels between them. You can have a stride. Or you can try to quantize x2 around x1, or both of them. And that's the way that you're going to reduce the cost of FlowNet C. Now you can use the benefits of FlowNet C. At the same time, it's not too costly. And you have the cost under your control. Depending on your device, you can play around with D, which is a hyperparameter. This is the entire architecture. It looks a little bit complicated at first sight, but in the end of the day, there is going to be 2 images that are going to go in. You're going to have a FlowNet C architecture, which is going to have some layers of this form, paying attention or computing the correlation with other pixels from the other image. And that one you're going to train. The flow that's going to come out of it is going to be looking not so great, but then it has this multi-stage nature that we know is useful for us to look globally and decide locally. We have been doing it for a while now when it comes to dense prediction tasks like segmentation, colorization, super resolution. It's the same ideas here. That multi-stage nature is going to help us. You get a flow out of it. You have the corresponding image for that flow. And then the other things that you don't know what they are, you know what image 2 is. It's your second image. You don't know how to warp it. And you don't know what is this brightness error. So I need to go through them. Let's say you have 2 images. This is the flow, which is a 2D object per pixel coming out of this step. So you have an estimate for your flow already. What you can do is you can look at your image 2, it's the second image, and then look at the pixel that is moved slightly according to this arrow, according to your flow. So this pixel that you're going to end up with is actually the original image. So there is going to be a correspondence between I1, your original image, image 1, and image 2 that you warped it using the flow estimation. And this is exactly that warped image that you're going to take and put it as another input to the rest of your architecture. So it's image 2, it's warped version, image 1, the corresponding flow is coming out of your neural network, the previous stage. And then the brightness error is this error that you're committing. This has to be perfect, but it's not going to happen. This is not going to end up being zero. You're going to make some errors. Take those errors into consideration. Don't assume they are zero. And these are going to be the inputs to the next stage. You're going to train that. You're going to get the corresponding flow. This one is the FlowNet S architecture. It's the architecture that we just went through from FlowNet version 1. The rest of them are warping and brightness error. Another stage, you get the flow magnitude, because these are 2D objects. You can look at their magnitude. In addition to the brightness error, are going to go in a fusion network, which is going to give you your final flow. But what is this FlowNet SD doing? It is trying to deal with the first problem, small displacements. So its job is to specialize on small displacement. The other part of your neural network, going deeper and then taking into account that you're making some errors, so things are not perfect, are trying to deal with the second problem, which is noisy artifacts. How does this FlowNet SD work? It's about small displacements. So it needs to be trained on a data set that has small displacements. And this is also a simulated version of the chairs with small displacements on a more homogeneous background. So you're going to train this on the small displacement type of data. That's why it's going to specialize in that task. The other one is whenever you have large displacements, you're going to apply a nonlinearity to your loss so that you're downweighting those large displacements. So you're forgetting about large displacements. In your loss function, you're focusing on small displacement. And in the end, you're going to get a method that is going to be as fast as you want because you can control its computational cost. At the same time, it's giving you very good estimates or errors. Any questions about FlowNet version 2? Was everything clear? In terms of the details of the architecture, I want you to go to the paper or to actually the source code that is available for it, and then look at how deep they are. What are your convolutional layers? What is your kernel size? Your number of channels? But I think it's better to get the picture, and then the rest of it you can figure out on your own. Okay, so far so good. So I want you to remember this step, the FlowNet correlation, because in the next paper, we are going to need that. It's going to be one of the layers in the next architecture.